before, and I hope it will still be useful as a reminder, because so far in this workshop, we have seen mainly propositional extent. So this is beyond part. I'm going to try and give a gentle introduction to what QBF proof complexity is. So what is the what are we talking about within QBS? Propositional formulas, you have a formula which is a tree, there are Boolean variables in the leaves, and then there are some Boolean connectives, and you want to know whether there is some assignment to the variables which makes the formula evaluate to true. So you could restate this as a QBF where you take the inner propositional formula and prefix it by this sequence. There exists x1, there exists x2, and so on. So now there are no free variables, everything is bound. And then the question is this sentence true or false? So you want to determine the truth of a sentence which has only existential quantifiers. And when you generalize this, you allow universal quantifiers as well. So every variable is being quantified either existentially or universally, and that's what gives you a QBF, a quantified Boolean formula. So in general, we are going to consider quantified Boolean formulas in which all variables are bound. So the formula is either true or false, and we want to decide which is which. In general, in this talk certainly, but also fairly generally, we are going to assume that all variables are quantified at the beginning. This is not necessarily the case. I mean, you could also quantify inside the formula, but it's, one could convert any formula easily to something of this form. So now the kind of things that you could express with QBF are no different from what you can express with propositional formulas and satisfiability. Expressiveness does not change. What changes is the length of the expression for the same condition. So it's a more succinct way of expressing things. And because the expressions are more succinct, it could be easier to prove lower bounds perhaps. But on the other hand, because there are these universal quantifiers, maybe there's more attention that one has to pay to that, and that could make things hard. So in general, deciding truth or falseness of a QBF is, we know this is p-space complete, so it's harder than that in that space. Okay, here just to remind you, say this again, that in this talk, I'm going to consider QBFs which have this very nice normal form, totally quantified, all quantifiers in the beginning. And the inner propositional formula I'm going to assume is in conjunctive normal and of clauses, although again, this is not absolutely necessary. So a very useful way to think about QBFs in many of these proof systems that I'm going to discuss later is to think of the truth or falseness of the QBF in terms of this two-player game. This is a very natural interpretation of when the formula is true or when the formula is false, where there is an existential player who claims that it is true, there is a universal player who claims the formula is false. So they play this game. Okay, I'll choose the value of my variables, existential variables. You are the universal player, you choose the values of the universal variables. The values must be chosen in the order in which the variables are quantified, right in the beginning. So they step through the quantifier prefix, assigning values to variables that they own. And then once you reach the inner propositional formula, all variables have been set. And you can just evaluate the inner formula and check whether it is true or false. So whether it's satisfied or not. So if it is satisfied, then on this run of the game, the existential player wins. Otherwise, the universal player wins. But winning on one particular run of the game is not something that we are interested in. What we are interested in is whether a player can always force a win, no matter how the opponent wins. So the existential player can always force a win if the formula is true, if the sentence is true, and the universal player can always force a win if the sentence is false. So the way the existential player would force a win would be described by some kind of a winning strategy in this game. How to choose the value of a variable, given the values of all the variables that have gone before, which have already been assigned before. And such a winning strategy is exactly what we call a model or a Skolem function. If the sentence is false, then there's the universal player has a winning strategy, which is a counter model or a Herbrand function. And then we have proofs which are trying to search for either models or counter models. So what we expect from a proof system is that the proofs should be short. They should be efficiently verified. The system should be sound. The system should be complete. And already at this point, given the interpretation of the QBF as a two-player game, you can see that there is for one thing, there is a symmetry which was not there in the case of SAT. In the case of propositional formulas, satisfiable instances are very easy to certify, and it's the unsat instances that require work. Here, there's no real difference between true and false in terms of how easy it is to certify, to give a model or a counter model. But verification certainly seems to be harder. Even if I give you a strategy and say that this is indeed a counter model, how would you verify that? This is not an easy task. So verifiability one has to pay attention to. Okay, so how would we design proof systems which meet these criteria? Start with a propositional proof system which can handle existential quantifiers and then try to add things to it, try to add more rules so that they can also handle the universal quantifiers. So this is one way to start, and this is how almost all the systems that I know of work. How would you ensure soundness? If you're trying to add on to a propositional system by adding new rules, you would want to ensure soundness by saying that, whatever rules you allow, at the end, once you have a refutation from that, you should be able to extract a counter model. So okay, I must say that here I am assuming that we are designing proof systems to prove that QBFs are false. We are only designing refutational proof systems. And there's really no difference between refutational and, because I can convert a QBF to its negation and then try to prove that that is false. So if for soundness, if there is a proof for some formula, then that proof is saying that there is a counter model and it should be possible to extract this counter model. And if indeed we can extract it, then that gives us a proof of soundness. So this would be one way in which you could ensure soundness, throw in rules which allow you to do this. But another way of viewing this would be to say that you throw in additional rules which have the property that they necessarily preserve the existence of a model, the existence of a existential player's winning strategy. So if at all there were a model, then as you add more and more clauses or more and more lines in whatever form using the rules of your system, that same model should continue to be a model. And eventually you produce a line which it's completely blatantly obvious that there is no model for it. For instance, the empty clause in resolution. So you could try to preserve the existence of a model and blatantly contradict it, or you could try to prove soundness in some other way by allowing the extraction of a counter. And how would you ensure completeness? Well, there are many different ways of, so how would you ensure completeness? By deciding what extra rules to throw in. There are many different ways in which this is done for QBFs. There's the expansion paradigm, there's the universal reduction paradigm, there's the literal merging paradigm, literal merging as well as building up. And I think these will make more sense through this example. So let me just give an example and then maybe we will. So here's a QBF. There exists an X such that for every U, there is a Y. And this triple XUY is then going to satisfy those three clauses, X or U or Y, X bar or U. So it's clear that the inner propositional formula is satisfiable. You can set Y to false and then X and U take opposite values and all clauses are satisfied. So satisfiability is not the issue, but because this U is universally quantified, it turns out that the universal player can always win this game. How are we going to prove this in a proof system? Well, here's one way in which we could prove it. We could say, okay, what does a for all U really mean? A for all U means for U equals 0 and for U equals 1. Something should happen. So just expand out the formula on the two choices of U. But if you expand out that formula, then the Y variable will have to get two copies. One from the copy corresponding to 0, one from the copy corresponding to 1.
So the point is you're really trying to prove the negation of this formula.
I'm trying to prove that this formula is false. Yeah, that the negation is true. I'm trying to refute things. So I'm trying to prove
So because yes.
Yeah. So when I completely eliminate the universal variable, then the existential variable which comes after it is going to have multiple copies corresponding to these different settings. And then after that, I have a purely propositional formula. So I have a propositional formula which has the X variable, the Y variable corresponding to U equals 0, and the Y variable corresponding to U equals 1. And I have copies of those clauses, one for 0, one for 1. And here in this example, I have used 4 of the resulting 6 clauses, and I have an ordinary resolution. So this is one way in which one could refute a QBF. Expand out all the universal variables and then do ordinary resolution or ordinary whatever propositional proof system you'd like to use. And this doesn't seem like a very smart thing to do because here there's only one universal variable and one existential following it. But once you expand, the formula is going to blow up. You're going to have so many more clauses. But the nice thing is that in many instances, it turns out that even though you would produce many more clauses, you are able to judiciously decide which ones of those to use. So you don't explicitly expand it. You use clauses which would appear in some expanded version. And often this is enough. Obviously not always, but often this is enough to produce small refutations. So here, this is finally a refutation because it has produced the empty clause. So it's the first idea that I mentioned, that you preserve the existence of a model, and finally it is clear that there is no model. Here's a different way of proving falseness of the same QBF. You start with the initial clauses as they are. You do some resolutions, and here the resolutions are being done on the y variable. And now you see what's happening here. I have this clause x or u from which I've derived x. Now the meaning here is that every time I derive a clause, I can add it to the inner propositional formula. And if there were a model, that model would also work with this clause add. So along with those initial three clauses, if I had added x or u, it doesn't matter. If the existential player could win earlier, she can still win now. But on the other hand, if she can still win now, then it is clear that the only way in which she could win is by satisfying the clause x. She can't set x to false and hope that your opponent, the universal player, is going to be very benevolent and nice and set u to false. The universal player is an adversary who is out to get you. So therefore, if she has to win and there is this clause x or u and u is universal coming after x, there's no other existential variable in that clause which she can use, then she has to set x to. So u can just be removed from this clause. Similarly, u can be removed from the other clause x bar or u bar, and now you have these two unit clauses which you can use. So this is the reduction rule. If you derive a clause, or in general it could be any more general line, in which there is a universal variable which is kind of trailing. In the order in which variables are played in the game, it's the last variable to be played in that particular line. Then it can be completely removed from that clause. It could be instantiated in either. So with this reduction rule, the reduction rule and resolution together gives us a sound and complete QBF system. Here's a third style of refutation. I try to resolve the clauses x or u or y, x bar or u bar or y. I try to resolve them on x. And normally this would not make any sense at all because the resulting clause has both u and the negation of u. But in this setting, there is a way to assign meaning to this fact that u and u bar are both there. It's not really as if it's a tautology because this clause has u and u bar. What it means is that I've written it here, I've denoted the so-called literal u star, which is it's a placeholder literal which says, okay, the player has a way of deciding the value of u depending on what is the value of x. And we allow such placeholder literals. So now it's not really a clause that is there. It's some kind of pseudo formula or whatever you may call, to which it is possible to assign this specific meaning. U star really stands for the existence of a non-constant strategy for playing the value of u. And with this, again, you perform resolution and you still have the same reduction rule. U, negation of u or u star can be removed from a clause if it is the rightmost variable in that clause. And finally, you produce the empty. Here's yet another way of doing this. It's in some sense, it is similar to the first method in that the universal variables don't explicitly figure in the clauses, in the lines. The clauses are only on the existential variables. But it is different. The universal variables in the first case appeared as annotations on top. Which copy of y are we talking? Here, the universal variables appear separately as partial functions. I can use the clause x or y in the context when u has been set to 0. When u has been set to 0, this clause can only be satisfied if the x or y part is satisfied. I can use the clause x bar or y in the context when u is set to 1. And now I can derive the clause y by resolving on x. And now the context is that this is useful when the value of u is 0 from the left or 1 from the right. In other words, I now have a non-constant function. U is equal to x. So this non-constant function that I've generated on the right is like the u star which is there on the left. But it is in some sense more general because on the left, u star just says non-constant, whereas on the right, I can even specify which non-constant function it is. Here it depends on one variable, it could be much more complex. So this is a different way of dealing with the QBFs and carrying forward partial counter models towards showing eventually that there is a full counter. So here are these 4 different ways to make things just a little bit more formal. The reduction rule, let me say a little bit more about it. In the 2-player game, if a partial run results in a purely universal clause, then the adversary, think of the universal player as the adversary, the universal player will falsify it. And therefore, if there is a trailing universal variable, as an existential player, I should assume it is going to be falsified. And so what this amounts to in a resolution style system is that whenever I have A or U, a clause of the form A or U where U is rightmost in the order, I can also derive A. But even in a non-clausal system, for instance, it could be cutting planes or something like that, I have any line in which U is a rightmost variable appearing in that line, then I could derive the line corresponding to U equals 0, and I can derive the line corresponding to U equals 1. Any instantiation of U is fine. So this is the reduction rule. And the merging rule, which produced those placeholders U star, basically this is saying that we should not think of U or U bar as a tautology, but as this placeholder. So formally the rule is specified this way in the context of resolution, that you can resolve on a pivot X, even though it merges a U and a U bar, provided U and U bar come after X. If U is quantified before X, it does not even depend on X. So X can be used as a pivot to tell you what is the value of U going to be depending on X, only if U is after X. So disallow certain resolutions, allow certain other resolutions. And these are the side conditions under which you can do long distance. Okay, so augmenting propositional systems to QBF, we can do expansion, we can do universal reduction, we can do merging, we can build up strategies. Universal reduction in particular is one of the most well-studied methods here. It works for almost all line-based proof systems. Take any line-based propositional proof system which is sound and complete, add the universal reduction rule, you have a system which is sound and complete for QBF. So this is a very mechanical recipe for producing QBF proof systems. Whereas expansion does not really have an analog because there is no concept of expansion in the propositional system. So there may be other paradigms also, but these are the ones which have been looked at in some detail, and especially in the context of resolution, which is the most well-studied propositional system, you can do all of these for resolution. So here's a picture of some of the proof systems for QBF. There's the expansion-based system, expansion for universal expansion and resolution. And then sitting on top of it, there's something called IR, which is instantiation and resolution. So it's a more efficient way of doing expansion. I mentioned that you don't have to really expand the whole formula. You can judiciously expand it. And in fact, not only can you judiciously expand clauses, you can even do partial expansions. So Y depends on all the universal variables to its left, but I may look at only the dependence on a few of those variables, not all of them. And this, at one level, it doesn't seem to make sense, but it can be justified by saying that when I derive something with such a Y variable, whatever I derive holds for all copies of Y which are consistent with this partial assignment to the left. So at one shot, you're deriving something which holds for many settings. So that is IR. Then there is Q resolution and QU resolution. QU resolution is the resolution plus universal reduction. There's LDQ, long distance Q resolution, long distance QU resolution. There's IRM, instantiation, resolution, and merging of a certain kind. There's MRES, which is the merge resolution, which keeps track of partial counter models on the side. So in fact, these below the E-Frege system, these are all systems which are loosely based on resolution. So if you try to ask what is the analog of resolution for QBF, there isn't one answer. There are these many systems are drawn here, and there are probably more. There are many ways to lift resolution to QBF. But they all sit within the system that we believe is very powerful, which is extended Frege and the universal reduction rule. And that sits within QRAT, which is the analog of the quantified analog of DRAT, which is the format in which proofs are output by many SAT solvers. So this is part of the landscape of QBF proof systems. I don't think it is yet there in Mark's Complexity Zoo. We need QBF people there who will volunteer to create the QBF proof system zoo as well.
In these drawings, never see the proof systems called G. Quantified proof systems.
We do. I have seen some work which talks about a quantified version of G sitting above QRAT, and I don't understand it very well. I know that it sits there above QRAT, and it has been looked at, but not in very much detail. So I've seen maybe 2 or 3 papers. How does one prove lower bounds for such proof systems, for QBF proof systems? One obvious way is to just say that wherever you have propositional hardness, it obviously holds for the QBF proof system. The obvious needs to be qualified a bit, which I will soon. You can also transfer computational hardness, and this is something that we do also in propositional systems. You could identify some kind of semantic hardness in the formula and try to use that to give a proof lower bound. So first, let me talk about transferring propositional hardness. Inside every reasonable QBF proof system, there is embedded inside a propositional proof system. The way I described the systems earlier, we in fact started with the embedded proof system explicitly and then augmented it up. But even if you thought of some other way of coming up with a QBF proof system, inside it there is a propositional system. And therefore, if I give you a QBF formula which does not have a universal quantifier, and then there is a lower bound for it, that would also work for, that is a lower bound for this system. So one small caveat here is that in principle, it is possible to design a QBF proof system which on purely existential formulas does not degenerate to a propositional proof system. It actually uses some higher order reasoning. I do not know of any such system. So from what I know right now, G for quantified. Oh, excellent. So Jakob asked me this question. Last year, I didn't know the answer. I still didn't know it now, but now I know. So then I should really go and read the quantified G papers more carefully. I see. Thanks. Yeah. So for G, anyway, we don't have lower bounds in the propositional case. So there's no question of transferring a propositional lower bound. That part, at least, I think, is still fine. Okay. Okay, so we already have these lower bounds, and in some sense, these lower bounds are not interesting. These are lower bounds which are coming from purely propositional hardness, and we want to understand where QBF is creating things that are hard. So the parts which are hard because of propositional hardness, in fact, we would like to think of this as in a real world system which has access to a SAT solver, since in so many cases SAT is considered easy, propositional answers will come for free. So that hardness I don't want to look at. I want to look at things which are hard, even if I had access to something which could answer SAT answer. So other propositional hardness methods, for instance, feasible interpolation, it essentially boils down to propositional hardness in the case of QBF proof systems. There are these game-based arguments in tree-like Q resolution. They again boil down to propositional hardness. So this is not the kind of hardness that we are looking for. We're looking for genuine hardness, and it's already a question, what exactly do you mean by genuine? So I mean, I don't have a precise mathematical definition. I have an intuitive feeling for, okay, this is not the hardness I'm looking for. I want to look for something like this. But there have been attempts to try and make this more precise. So one way of making this precise is to simply throw in an oracle in the proof system. With access to an NP oracle, if a formula is still hard to refute, if it still requires long proofs, then this is not propositional hardness, because propositional hardness part, the oracle would just give the answer in one step. So NP oracles could be built in, but how does one build in the NP oracle into the system? One way would be to discount any deduction step where the reasoning that has been employed is purely propositional. So for instance, in the system of resolution plus universal reduction, this means you only count the reduction steps. The other steps are resolution. Resolution is propositional. So I don't care how many resolution steps you use, but how many reduction steps do you really need? That's going to be my complexity measure. In systems with merging, also you could formalize this in some way, and then so we have ways of talking about genuine QBF hardness. And what we are trying to do here is to say, even assuming for whatever reason SAT and SAT is easy, what is it that makes these formulas hard to do? How does one transfer computational hardness? So, techniques for lower bounds. Propositional hardness is boring. So the next thing, can we transfer computational hardness? I mean, one of the obvious ways of doing this in the propositional setting is to do feasible interpolation, which transfers a circuit lower bound to a proof lower bound. But that does not transfer to a genuine lower. It transfers only to a propositional. So I want a different way of transferring computational hardness. And this comes very naturally from the two-person game. If you give me any refutation of a QBF formula, sitting inside that refutation implicitly embedded in some way, there should be a description of a counter model, of a winning strategy for the universal plane. Now, maybe I try to examine the proof and extract that strategy, and the strategy size in some sense will be related to the proof size, but if the strategy is hard, then there cannot be a shortcut. So what we want to do, this is the key idea. The proof, every proof contains information about a counter model. Depending on the rules of the proof system, for each proof system, try to identify what is the correct circuit model in which the counter model can be described. The circuit model will depend on the rules of the system. And refutations in P are going to yield circuits in this model M for the counter models. Now you find a function which has small circuits, and which is hard in this particular model. So these models are they're always going to be much more restricted than general circuits. So we want a function which is easy with general circuits, but which is hard in this particular model. If we do have such a lower bound, then we can very easily construct a sigma-3 formula. We don't even need too many alternations. A sigma-3 formula which says something like this. There exists an x such that f of x is 0 and f of x is 1. So I write this here by saying there exists an x for every value of b, the circuit which computes f on x, it evaluates to b. And this is obviously false. The only possible winning strategy for this is something that computes the function f. And if f cannot be computed easily in M, then there will be no short adaptation. So in fact, using this thing, this is something that was shown some years ago, that in Frege style systems, Frege plus universal reduction, there are only two sources of hardness. Either there is an embedded propositional hardness, which goes away the moment you give an oracle, or there is a circuit lower bound. So computational hardness is the only way in which something could be hard for a Frege system. It turns out that something very similar to this also holds for other systems. I'm running out of time, but maybe let me spend a little bit of time on the second point here. What they showed was that in these Frege plus reduction systems, from any proof you can extract a set of witnessing circuits and a proof that they are indeed witnessing circuits. And therefore, hardness comes from either there being no small witnessing circuits or it being hard to prove that these are witnessing. That's that. So with this, for instance, we have lower bounds even for AC0P Frege in the QBF world, which we don't have in the propositional. Let me skip what is going on here. Size width. Maybe we'll come back to that later. Semantic hardness, there has been some attempt to identify semantic hardness because there have been situations where the counter models are completely trivial. It's not that the counter models are hard to compute computationally, and there is no underlying propositional hardness at all, but they are still hard in the system QUris. But then it turns out that they being trivial, it was a question of the right model. So it seemed that they were trivial because they were projections. But the moment you say that you want a multi-output decision list, they became hard. So really the work is on identifying the right model which corresponds to the proof system. So there are various questions that one could ask about QBF proof systems. In particular, the power of algebraic reasoning has not been studied so much, but we will hear more about it soon. We don't have those many candidate hard formulas. It would be good to have more. Formalizations of the random formula model, I think there's some more work needs to be done, and so on. So maybe I'm going to steal into some of Abhimanyu's time, and I want 2 minutes more to set up one more thing about QCDCL. So this is amazing that we have had a proof complexity workshop in day 4 and CDCL has not really. So conflict-driven clause learning, which is used so much in SAT solving, and we know that it is equivalent to resolution. It's a non-deterministic algorithmic template. The question is, what is the analog of this in the QBF world? Are there QBF solvers which are based on CDCL? Yes, there are. But the first question we should ask is, what is even a conflict from which you're going to learn something? In the world of satisfiability and unsatisfied, an assignment which falsifies a clause is a conflict. Whereas in the QBF world, an assignment is always a conflict. If it satisfies everything, then it rules out some counter models. And if it falsifies a clause, it rules out some models. Either way, you can learn something from it. So what is the correct lift of CDCL to QCDCL? This is not clear. What is the correct lift of resolution to Q resolution? This is not clear. I showed you a whole zoo. Therefore, what should we be even aiming for when we say, what is the analog of resolution equals CDCL? There are way too many questions there. Somebody else wants me to stop. Okay, so this was the picture of QBF proof systems, and here are these two algorithms that I've mentioned, which are for QBF solvers. There is one particular family of CDCL-based algorithms, QCDCL, which are explained by the system long-distance Q resolution, which is why I even wanted to mention long-distance here in the first place. But they are not equivalent. QCDCL algorithms are probably weaker than LDQs. There's another expansion-based solver, which is explained by universal expansion. Again, it's not clear that they are equivalent. So there is more work to be done even in understanding the relation between CDCL and CDCL style algorithms for QBF and CDCL based proof systems. A lot of work on this has been done in the last 3-4 years. Olaf would have been the perfect person to be talking about it because he's done a lot of it. He's not here and I dismiss this now in this 1/2 slide. Okay, and there are more questions to ask, but in the next 2 talks, we'll be hearing more about these 2 aspects. One is the CDCL style QBF solver, and the other is the algebraic reasoning and polynomial mechanics. Yeah, thank you.
Okay, Meena. We can do one quick question while Abhimanyu sits up. Is there a nice example of a hard family of formulas where the quantifier alternation is a parameter?
Yes,
Where there's a sequence of formulas of more and more quantifier alternations?
yes, yes.
Where the hardness seems to come from, increasing hardness comes from the increasing
Yes.
quantification rather than something else?
Increasing quantification, I don't know. There are formulas where actually you need omega n quantifiers. I mean, they are described naturally in that way. These are in fact, one of the earliest formulas for which hardness was explored. These were proposed by Kleine-Buning, Karpinski, and Flugel, the KBKF formulas. And they have, I think, n alternations and theta n variables. And they are very hard. But there are other formulas also in this of this type. Specifically parameterized by, yes, so actually KBKFT you could also parameterize. There is another set of formulas which was proposed by Janota and Marcus Silva, I think, where the number of variables and the quantifier alternation, I think you have a little bit more slack in how you trade it. And they are also hard for some of the simpler systems. For bounded alternation formulas, we have some specific lower bound techniques proposed by Olaf and a couple of his co-authors. They work only for sigma 3 formulas of a particular type. So the ways of proving hardness, of course, diminishes as you go higher up.
Then I think we'll stop here.
Yeah, thank you.